welcome everyone to the Building Conversations, Passive House Canada Building Conversations monthly webinar series. We took July off and we are back again in August here, but back to our monthly again. So welcome back for those of you that you regularly attend, and for those of you that are new, we've got a very quick little housekeeping to get through before we start our session. So on the Zoom chat line, you're welcome to put in any questions for today. We're going to run at about 45 minutes and then take questions afterwards. And sometimes if a question pops up in the middle of a conversation, we can address it then as well. And maybe if we have some time at the end, you can also put your video on and ask the question yourself, hoping we've got some extra time depending on questions. Just for your information, this is going to be recorded and you can also view it on YouTube afterwards. Any questions or any concerns that you have during trouble during the webinar, feel free to just send me a message in the chat section and we'll help you out. So with that, I'm going to pass this over to our CEO, Chris Ballard. Chris.
Well, thanks, Deb, and welcome everybody who's here today. Listen, I'm going to do my best to keep it to 45 minutes of discussion, but we've got such an interesting guest with us today that you can't hold me to it, because when Harold starts talking and we start learning about his past and the things he's working on currently, I suspect we might go a little bit over. But let me first start with a land acknowledgement. I just want to say that I want to begin, of course, by acknowledging the Indigenous peoples of all the lands that we are on today. And that while we meet today on this virtual platform, I want to take a minute to acknowledge the importance of the lands which we each call home. We do this, of course, to reaffirm our commitment and responsibility to improve relationships between nations and to improving our own understanding of local Indigenous peoples and their cultures from coast to coast to coast. We acknowledge the ancestral and unceded territory of all the Inuit, Métis, and First Nations people who call this land home. So thank you again for everyone who's here today. My guest today is Harold Orr. We had Mr. Orr with us back in February, and we had such a great outpouring of interest that we brought him back for round two. We're not sure where we're going to go today in our conversation, but Harold has such a wealth of information, not just about how Passive House got to where it is today, but where it's going in the years ahead. I'm sure there'll be lots of that. I want to tell you that Harold is from Saskatchewan, and he is an Order of Canada recipient. He was awarded the Order of Canada in November of 2019 and invested in February of 2019. I think the best way to introduce Mr. Orr is to read the paragraph that came with his investiture. Harold Orr's efforts have been integral to improving energy efficiency and conservation in Canadian homes. As a housing engineer with the National Research Council, he was a key driver of the Saskatchewan Conservation House project, which led to the establishment of new national energy conservation protocols for Canadian buildings. His innovations, which include new insulation techniques and materials, air sealing and efficient ventilation, blower door testing, and heat recycling, serve as worldwide models for energy efficient housing. And I'll attest to that in that Harold and his work have been acknowledged by the Passive House Institute as being part of Passive House Institute's DNA. So, if anyone ever says to you that Passive House is a foreign concept, it's not, right? A lot of its roots are right here in Canada, right here with the work of Harold Orr and his colleagues many years ago. So I'll just leave it there. So let's get into our conversation. We can turn off the slide and we'll bring Harold on. And welcome again, Harold. And looking forward to a good conversation. So I'm hoping everyone can see us right now. Deb, I see your slide up there. Hoping people can see Harold and I clearly. You know, Harold and I started a conversation the other day with a bit of a discussion about what's happening to the weather. We're all aware of the United Nations Code Red for Humanity report that came out earlier this week. Harold and I talked a little bit about that, but then we got talking about local weather. Where I am in Canada, we were experiencing a lot of flooding. You know, those 100-year storms that seem to be showing up once a month. But Harold, tell me, what's happening in Saskatchewan?
Well, we have had this summer one of the driest years ever recorded. We're setting a record for this, and unfortunately, since the dirty 30s, when farming was on the prairies was just starting, they didn't have the techniques that they have now. And so now they are using different techniques in farming. And the result is that because we have very, very low rainfall precipitation this year, they are in fact getting some crop, but it's very, very low to normal. I was just talking yesterday rather, to a farmer, and they were saying that they were getting 5 to 10 bushels per acre, whereas normally they would get 40 to 60 bushels per acre. Wow. So it's very, very low, but there is in fact some crop, which compared to the
dirty 30s, as they were known as, the years of drought, where there was nothing and we lost our topsoil.
That's right. Well, yeah. Now they don't leave the fields barren of any crop material. They in fact try and keep it covered so that the wind doesn't blow the topsoil, and we don't have the drifting that occurred during the 1920s.
Right.
But it's 1920s and 30s. But this is likely to be the driest year ever recorded for this area of the country.
Which leads us to, you know, that topic that brings many of us together today, and that is, you know, the role of housing in addressing the climate crisis. But maybe for those of us who aren't aware of your background, can you give us a bit of a synopsis of how did you come to that point where, you know, you were awarded the Order of Canada? What led you to work on high efficiency buildings? How did you get there as a young engineer?
Well, I started out being a carpenter. My father was a carpenter. My grandfather was a carpenter. My great-grandfather was a jointer, a Finnish carpenter. Mm-hmm. And so when I was 12 years old, the summer that I was 12 years old, my father built a house for us. And I was one of the carpenters, if you like, on the job. So 78 years ago, mm-hmm. I started doing carpenter work. And I put myself through university doing carpenter work. And in between time, I took a period out of my education and worked for the provincial architect's office in Regina. And so I have 3.5 years working as an architect, architectural draftsman. And I've been in the building industry since, well, 1934.
Wow.
So anyway, when I was in university and getting my first degree, one of the problems was, after I got my first degree, one of the problems was in calculating the heat loss from buildings, we could calculate the heat loss through the walls because we knew how much insulation was there and the R value of it. We could calculate the heat loss through the ceiling because we knew the insulation there. But when it came to air leakage, nobody had an idea. And ASHRAE, the Association of Heating, Air Conditioning and Refrigeration Engineers, had an idea, and they said, you take a feeler gauge and go to the windows and measure the crack around the windows and the doors. And they had a formula, and they stick these numbers into the formula. You turn the crank and out came a number. And the number didn't seem to bear any resemblance to what we knew in fact. And so one of the things my professor suggested, why don't you build an instrument to measure how fast the air is changing? So I worked on an instrument. I built an instrument that would measure how much helium there was in the air. And we would take a house and dump 100 cubic feet of helium into the house, and then we would measure how fast this disappeared. And as this helium disappeared, we would assume that the air was leaking at the same rate. And so I got my degree, used a master's degree with this instrument. And I was doing my work at the National Research Council because the university just didn't have the equipment I needed. And so, but the National Research Council had the equipment, and I was using their equipment, and I got my degree. And when I got my degree, they put me on staff and started to pay me for doing the same thing. We started working on better methods of measuring this. And so one of the things we did there was to change from helium, which we'd been using, because we used quite a large amount, 100 cubic feet, a full bottle of helium, and dump it into a house. And we went to sulfur hexafluoride. And the reason was that we could do the same test with a teaspoonful, 5 cubic centimeters of sulfur hexafluoride converse rather than 100 cubic feet of helium. And now this solved another problem for us. One of the problems was when we put the helium in, it was very concentrated. So this concentrated helium would go into cupboards and closets and dead air spaces and whatever. And then as we flushed it out of the rest of the house, this helium would start to come out of the woodwork. So what are we measuring? Well, we're measuring the level of helium, but what has that got to do with ventilation? Well, it's a very complicated formula, and we didn't have an equation for it. So we switched over and made an equipment with one of the first computers that was available that you could program to do work for you, that you could actually push buttons if you like. And what we did was connect this to a gas chromatograph, and we would take a sample of air, measure, separate it, put it through the gas chromatograph, which would separate the sulfur hexafluoride from the air. And then we'd measure this peak of sulfur hexafluoride and the peak of the air. And then we'd calculate what the level of sulfur hexafluoride was in the house. 15 parts per billion, I think was the number we used. And then since it was likely below this, we then calculate how much we had to inject to bring it up to our level. And we'd inject this amount of sulfur hexafluoride, have the furnace fan circulate it through the house, and then take another measurement and do the same thing. And so now we keep it at this level so we don't have this problem of it going into the woodwork and coming out. And what we were finding was that the numbers that we're getting for our ventilation were very much higher than had been anticipated. And so the problem was with this equipment was that in today's numbers, the equipment that we were using was about $5 million worth of equipment. And it took us a week to put this equipment in the house and run it for a week. And then we do the numbers and we have a number for this house. But you simply can't do that on all the houses. And so I invented then the blower door, where we put a temporary door in the doorway. We blow air out of the house. We measure how fast the air is going, and we measure the pressure that this creates across the house. And now we can go back and calculate how big the hole is that is in the house, if you like. And so this resulted in our better knowledge of how where the heat is going in the house. And as a result of this, we now know that about 30-something% of the heat loss that we lose from a house is due to air leakage. 30%.
Wow. Yeah.
There's 10% through the walls, 10% through the ceiling, about 10% through the windows, 30% through the basement, and about 30% through air leakage.
Wow.
So now when we start looking at this in terms of how do we reduce the thing, at this time came up the problem with the Iranian companies wanting more money for their oil because we were using oil. And so overnight, they doubled the price of their crude oil, which doubled the price of the gasoline. It went from 35 cents a gallon to 70 cents a gallon. And you went in to get oil and gasoline in the car, and you didn't have enough money in your pocket. So you put half a tank in and complained to the gas station attendant. What's the price? What's this with the gas price? And then if you were really diligent, you called up your member of parliament and gave him what for. Well, at that time, the provincial government in Saskatchewan asked the Saskatchewan Research Council to design and build a solar house appropriate for Saskatchewan. Now, we did some quick back of the envelope calculations on this, and we found out that because the solar energy we get in the wintertime is not very much, it's on the low end. And so if we're going to heat the house with solar energy, we're going to have to collect the heat in July, August, September, and store it to heat the house in November, December, January, and February. And when you did the calculations on this, you need an Olympic swimming pool for every house to store the hot water in. And this swimming pool has to be super insulated, and it has to be sealed so that it can't evaporate. And that doesn't really make a lot of sense. Although some of the fellows down in Toronto area tried this. North of Toronto, they built what is called the Provident House. And they had a house that had the roof that sloped towards the south. And the whole wall was covered with solar collectors. And the basement was made bigger and normal. And it was the water storage for the house. And then the house was built above this, two-story house built above this. And how do you seal this hot water from producing steam that comes up into the house. Well, that wasn't very effective. And I think they misnamed the house. They called it Provident House, but I think they should have called it Prove It Don't Work House. And so anyway, this didn't seem to work. So we were asked to, since the Saskatchewan Research Council didn't have the expertise, they asked a number of people in the building industry to sit in on a committee to help design this house. And I was one of about 12 or more people on this committee. And so at our first meeting, somebody suggested, well, let's build a house with our 20 walls. And I said, well, I don't think that's going to do it. I think we should do it with 40. But I said, one of the problems, of course, was the air leakage component of this. How do you keep the air leakage of the house down to a suitable level? And if you do keep the leakage down, then how do you have enough fresh air? And so one of the, Rob Dumont and one of the technicians, Dick Van E at the university, a technician at the university, went on the project of, they built an air-to-air heat, the first air-to-air heat exchanger for houses.
Mhm.
And as a result of this, Dick Van E started the company, the Van E Heat Exchanger Company. But anyway, when it came to making the house tight, since I was a carpenter, I have a carpenter's license, I decided to go down and personally install the air vapor barrier on the house. And I took a technician from NRC and we went down and installed the vapor barrier very carefully. And we did this. And when we did a blower door test, the house came in at 0.5 air changes per hour at 50 pascals. And at that time, it was likely one of the tightest houses in the world.
Mhm.
But we spent an awful lot of time sealing the vapor barrier around electrical boxes, around joists, and because the joists on the second floor all went through the vapor barrier.
Right.
We spent an awful lot of time and work trying to seal this the best we possibly could. So one of the things we got there was, how could we do this better? And one of the ideas came up, well, we built the Saskatchewan Conservation House, and one of the things we wanted to do, could we do this on a retrofit house? So we borrowed from CMHC a house that had been the manager's house here in Saskatoon. And we did what is now called the chainsaw retrofit. And
That's scary.
we didn't use the chainsaw, but we did actually cut the eaves and the overhang off the house. So we now have a nice, neat box. And we put, where we had the raw edges, we put a piece of plywood on that, covered that up. And then we wrapped the roof with 6 mil poly and then joined it to a piece of poly, which we wrapped the walls of the house, and we sealed that to the foundation. And then we went on the roof and we put a 2x8 at the peak of the roof, one at the edge of the roof, and one halfway in between, and then new rafters. And we filled this space with our 40 insulation, and then put a new roof on it. And we did the same thing on the walls where the rafters stuck out. We nailed a 2x4 to the side of the rafter and hung it down. So we had a foot wide space on the house, and we put R40 insulation on the walls until we got to a foot above grade, and then we went to pressure treated wood and put insulation to a foot below grade. And at this time it was difficult because CMHC and other builders had recommended that you do not insulate your basement walls more than 2 feet below grade. Otherwise, the frost will go down and you'll freeze the footings and the house will heave and problems. So one of the things we did on this particular house was we insulated the basement walls with R40 right from the floor down to the main floor above, down to the concrete floor. And we put 3 inches of blue styrofoam on the floor, R15 on the floor. And we glued plywood on top of that. And so we had it very well insulated. And we had a driveway up the side of the house. And one of the technicians we had the job every day going by in the morning. If there was snow on that, he kept the snow off this. And we put a string of thermocouples down beside the house and a foot away and further away so that we could tell what the temperature was down our thing. What we found out was this super insulated house, the frost doesn't get anywhere close to the footings, even with a well insulated basement. And so that has been gotten rid of. Anyway.
If you can, what you proved, if you can do that in a cold climate like Saskatchewan, you can do that virtually anywhere in Canada.
That's right. Yes.
Yeah. Good.
So anyway, but this is this older house with older houses, and I recommend we've done this numerous times. I did this on a fourplex in Regina. And we wrapped the roof and we wrapped the walls, and we went from the lower door test before we started was 11 air changes per hour at 50 pascals. Wow. When we finished, we were down below 2 air changes per 50 pascals. We reduced the air leakage by 85%. So you can do it. But when you come to a new house, you've got different problems. And the problem normally in the new house is the vapor barrier runs along until it comes to a partition wall. And particularly on the ceiling, the vapor barrier runs along till you come to a partition, and then it's broken by the partition wall. And CMHC now requires that you put a piece of vapor barrier over top of that partition wall. But is it sealed on both sides? I don't think so. And the result is that we have, in a normal house, you have about 160 lineal feet of interior partition. There are 2 sides to it, that's 300 feet of crack. I've been up in the attic and I've measured these cracks, and my estimation is that they average about 1/16 of an inch. And 1/16 of an inch times 320 feet of crack makes a hole that's big enough that you can crawl through. And that's the problem that we have in construction. And so how do we build a house that doesn't have this problem? Well, one of the things we did was then to design what is now known as the prairie double wall. And the prairie double wall has the outside wall of the house is the structure, of course. And it has a double wall, and the inside wall is the structure. The outside wall is a light frame. Now, when we do this, when the wall is being built on the floor, we square it up ready to put sheathing on the wall, just as we normally would in terms of a house. But before we do this, we put the vapor barrier on the top surface of the outside wall. And we extend it out so it's 8 inches or so all the way around the wall. Then we put sheathing on it. And when we do this, then we build the outside wall directly on top of that. This makes it, you're sure that the windows match and the doors match and so on. And now you lift it up and make space for between the two walls that you want. 5.5 inches for an R20 bat, more for thicker, more insulation, whatever. Anyway, then you fasten the two walls together by putting a piece of plywood at the top and the bottom of the walls. When you stand the walls up, now the walls are higher by twice the thickness of the plywood that you hold the two walls together. This has a major advantage because when you put the roof trusses on, the roof is now 3/4 of an inch higher than it normally is. So you can put the vapor barrier on the ceiling and drywall on the ceiling before you put any interior partitions in. And this means that if you do it right and can buy it, you can put one sheet of poly on the ceiling instead of 45 pieces of drywall, vapor barrier on the ceiling. And you can use 14-foot sheets of drywall. And when you get finished, you pick up the scrap in one hand and put it in the dump. Instead of when you have all the partitions there and when you get finished putting drywall on the ceiling, you got a half-ton truck full of drywall garbage.
Right. So this is a major advantage is what you're saying, using the prairie wall system and not building the interior partitions until after you've drywalled the ceiling. It's obviously waste. It would also be time, wouldn't it? You could do this much faster.
Oh, you can do it very much faster. And in fact, I watched a couple of drywall people put vapor barrier and drywall on the ceiling in about 3 hours. And they're working on stilts. So they were up there working on the thing. And man, they went at it putting 14-foot sheets of drywall on the ceiling. And they were finished in no time.
Yeah, yeah.
And people who've done this tell me that they save money every time they do this.
Right.
In construction.
So those of us in the passive house world have certainly heard of the double wall. And is this the double walls that we're used to all, it sounds like they have their heritage in the work that you were doing. So not only did you invent the blower door test, but you were instrumental in helping design one of the key ways that we're building passive houses today.
Well,
through the double wall.
Yes.
Yeah.
So
very good.
So anyway, with the vapor barrier on the outside of the inside wall, the electrical boxes and so on don't have to go through the vapor barrier. Right. This is major reduction in work for the electricians. They don't have to use poly pans. The drywall people, it saves time and effort for them because they put the vapor barrier on the inside and have to seal it around all these poly pans and so on. And if they're doing it properly, they have to be very careful in terms of cutting holes for electrical boxes and so on because they don't want to cut the vapor barrier. But they've got these sharp tools and it's a real problem. So no, the double wall moves that problem to the outside of the inside wall where it's protected by the sheathing that we put on top of it. And it works great and it saves money and
great.
Time.
What's the limit? Are there limitations to this wall system? I mean, how high can you go with this type of system? Well, looking 2-story, 4-story.
you can, since the inside wall is actually, it's the same structure as we normally build in, have been building for many years in structures. And basically with wood frame, they're talking about 6 stories, but
Okay.
now they're increasing that. And I think they're going up to 12 stories.
Wow, that's significant. You know, before the show began, you and I were talking, well, you were telling me about some of the back of the napkin calculation work you were doing about with today's price of lumber and attaching styrofoam to the outside of walls, and why this system is some of the work you've been doing, some of the calculation you've been doing to reduce costs. So can you run that past us again? You were talking about 16-inch on centers and 24 on the outside. Just share that thinking with folks today.
Well, I just looked at the price last week of 2x4s, and a 2x4 stud is $6.49. A 2x6 stud is $10.99, $11. If in a 4-foot panel, there are 3 studs at 16 centers. So 3 studs come to $19.47. And if I put studs at 24-inch centers on the outside wall, that takes 2 studs. So 5 studs out of 2x4s is $32.45. If I take a 2x6 at 16-inch centers, 3 studs are $32.97. So 3 studs are more expensive than 5 2x4 studs.
Mm-hmm.
So the double wall is cheaper than building with 2x6 studs. Now, if I add 1.5 inches of styrofoam, which is $1.50 a square foot, at least $1.50 a square foot. The styrofoam is 5 times more expensive than fiberglass per square foot of R value. So if I add styrofoam to the outside of the 2x6 stud, I can replace it with an R7. I could replace it with R35 of fiberglass for the same price. And somebody's got to tell me, why is R7 a better bet than using R35?
Mm-hmm. Yeah.
So with the double wall, there's other problems. When you put 1.5 inches of styrofoam on, now you have to use fasteners to hold your siding on that are 1.5 inches longer than normal. Well, that makes a bit of a problem because you're fastening the siding to nothing that is steady. Whereas if you're nailing it directly to the stud, you've got something solid there to build to. Mm-hmm. So if you were going to put, in fact, as if you were going to go the stage further in terms of your 2x6 wall with styrofoam, suppose we put 4 inches of styrofoam on the outside.
Mm-hmm.
Oh my goodness, how on earth do you fasten siding to it? Well, we got to put strapping on the outside. You put strapping on the outside, and did you know that 1x4 strapping is almost the same price as 2x4s?
Right.
So if you put strapping on the outside and put it at 16-inch centers, I've doubled the price of the wall, basically.
Right.
And so I've got problems here. So why don't I build a double wall, put a 2x4 out there where I can fasten the siding to it and have it really good to make it.
Good. We have a few questions that are coming in, and we'll start a few questions from the audience in a minute, Harold. But one of the questions I'm gonna preempt it because I think it's a good question. One of the folks is saying that the prairie wall system sounds very much like the R2000 wall system, the audience member is wondering, that the R2000 system never really took off, there are people who say it didn't really save a lot of energy. And he's wondering, is that because of the other critical building components like windows and doors and air tightness weren't improved?
Well, I suspect my estimation is that really we have not improved the air tightness of houses appreciably. And air tightness is in any house, any building that you go into, the largest single component of heat loss is air leakage. And so we need to put more money into making the house airtight. And it seems to me, from my experience, the easiest way of doing this is with the double wall. Now, we had a builder in Winnipeg. I think they're no longer in business, but back 30 years ago, they Flair Homes in Winnipeg were building double wall houses, and they were doing what I believe has likely been the tightest houses ever built. And they had a little trick on this. What they would do is when they got the house to the stage where they could do a blower door test, they would invite their other crews that were building houses to come and witness the test and cheer or jeer as the test went on. And they were routinely building houses at 0.12 air changes per hour. That's 5 times tighter than the passive house 0.6 air changes per hour.
Right. And yet today we have builders who complain that they can't meet that passive house standard.
That's right.
Yeah.
And they were doing it routinely. So don't tell me that can't be done. I think it can be done, but you have to, unfortunately, we don't have, people who are trained to put in just vapor barrier.
Right. Good. That's a really good point.
And the vapor barrier is like in the double wall, we have to have crews that normally never touch vapor barrier, put it in. And that's the carpenter crews building the outside walls. We have to have them put it in. And I don't know if they could do it properly.
Yeah, without specialized training.
That's
so
right.
Let's take a break here for a second, and I'll go back to Deb Knopp, who has some questions coming in. Deb?
Yes, we do. So Mr. Orr, this question is for you. What was your overall favorite discovery in terms of conservation, designing, or building construction?
What was my favorite?
Your favorite discovery in terms of conservation, designing, or building construction?
Well, I think my thing is that air leakage is the major component of reducing energy consumption. And,
Okay.
and how you get air tightness, that's a really good question, particularly if you're building conventional construction. You've really got an awful lot of work to do to seal it. In normal construction, how do you seal between the top of the floor and the basement? How do you seal the vapor barrier from the basement to the basement floor? How do you seal where the partitions meet the exterior walls? How do you seal where the interior partitions meet the ceiling? There are all these components, and they're all a major problem in normal construction.
Mhm. So air sealing, the importance of air tightness. We get that.
Right.
Good. Next question, Deb.
Yeah, so this one came in a little while back, and just to make sure that it was addressed, a lot of people complain about the difficulty of achieving the 0.6 ACH. What materials did you use to achieve 0.5 ACH at that time?
We use 6 mil poly
The-
and acoustical sealant. We joined every piece of poly to the next where we could overlap it, and we made it on a stud or a solid material, put one piece stapled to the stud, put a bead of acoustical sealant on it, and stuck the second into it. And then we nailed drywall or some other solid material over top of that. So all the joints have to be sandwiched between two structural components.
Wow. So much easier today with all of the tapes that are available that allow you to seal your poly together.
Right.
Interesting.
Great. We had another question here back to the prairie wall system. Is it more effective than the Larson truss system?
Well, the Larson truss, with the Larson truss, you can put the vapor barrier on the exterior of the interior wall. And I don't know if that's, I haven't seen the specifications on the Larson truss, but you could do that. And the Larson truss goes out, could go on the outside then and make space for your insulation, and it, in some respects, protects and holds the vapor barrier in place. But then you have the problem of how do you join that vapor barrier on the outside wall to the vapor barrier on the ceiling? At the top plate, do you just seal the vapor barrier to the top plate and then go inside and seal the vapor barrier on the other side to the top plate? It would be much better if it could possibly go across and the two lap, and you can seal the two components. But outside of that, I see no reason why you couldn't use the Larson truss. The difficulty I have with the Larson truss is, have you ever tried to put insulation in to Larson truss? Because you've got all these plywood baffles on every stud. And why do you have all these baffles there? With a 2x4, if you're using a 2x4 stud on the outside, why do you need to have 3 or 4 or 5 baffles to seal it to the interior wall? Why don't you just fasten it at the top and the bottom?
Mm-hmm. Like the prairie wall system you're talking about. You were describing
like the system, yes. Why don't you just use the same? A stud, a 2x4 stud spans 8 feet with no support at all. Why do you have to support it 3 times or 4 times or 5 times?
Good. That's great.
And if you're going to use the Larson Truss, my suggestion would be that you really need to likely use cellulose fiber, blown in cellulose fiber in the stud space, because you simply can't put bats in there and make them fit properly.
Okay. Very good. Anything else now, Deb? Because I have one last question for Harold before we wrap up that may take some time.
Yeah, just there's no direct questions other than many comments saying that I am listening in awe, and thank you very, very much, Mr. Orr. But other than that, there's no direct ones.
Yeah. Well, yeah, and thank you on behalf of the high performance building community for the work that you've done on developing, inventing the blower door. I don't know how we could do what we're doing today if we didn't have an inexpensive way of testing for air tightness, quite frankly. So that's fantastic. But you know, Harold, when we signed off in our last discussion, people were really interested in knowing, what are you up to today besides calculating the cost of a 2x4 versus 2x6 on today's lumber prices? What are you working on today? What interesting things are you up to right now?
Well, we have, I think if you work on it, we've solved the problem of the air tightness. We can, with the prairie double wall, we can build walls if you want R40, R50, R60, you want R70, we can do it R80 if you want. There's no problem that way. Okay. So this has reduced the heat loss from the walls. If we use high lift ceiling trusses, we can put, how much did you want in the attic? We can put R100 in the attic, no problem. We've got the walls solved, the ceiling solved. Basements are a bit of a problem, but I like pressure treated wood foundations. They don't have the thermal conduction that concrete does, and they make excellent basements. Now, the thing that is still missing here, though, and we haven't done anything for 30 years, is windows. And Rob Dumont was asked, what's the #1 problem with building houses today? He said, #1, it's windows. #2, it's windows. #3, it's windows. And I would say that's still likely the problem. Now, there is a thing happening here. They're starting to make evacuated windows. And what they do is they take 2 sheets of glass and they put little hockey pucks, very, very small, about 1 millimeter in diameter and 0.5 millimeter thick, between the sheets of glass, and they put them about 1.25 inches apart. And then they put the 2 sheets of glass, and then they draw a very hard vacuum. And before they do this, of course, they put low emissivity coatings on the glass. And this, when they do this, 2 sheets of glass give them about R20. And you put 3 sheets of glass and you get R40. And that, if you change your windows and put R40 windows in instead of the R5 or 4, R6 that you get with triple glaze, I think that makes a major difference.
So that's the next big thing, is what you're saying, is the this new generation of windows that we look forward to. Have you,
yes.
have you had a chance to work with them? Or are they still in the pre-production phase? Are they being made anywhere?
They are being made in China, and they're also being made in Japan. And I don't have the names of companies, but my son has been dealing with a company in China, and he has bought building materials in China and brought them over to Canada, and at a fraction the cost of Canadian materials.
It shows there are still areas that we can improve on. I'd like to end it where we started off by, if you could say one thing to the builders, the building industry, or to politicians, to the public about the importance of the types of buildings you've been involved with all your life and the linkages to climate change, what's your message to all of us?
You're going to have to, if you build properly tight, you have to ventilate. And if you use an air-to-air heat exchanger, that would be a good idea. That's an excellent idea to provide ventilation. Unfortunately, most heat exchangers are using what is known as the cross-flow heat exchanger.
Mm-hmm.
And about the maximum efficiency you can get with that is about 75%. And what they need to do is use a counterflow heat exchanger, which you can get efficiencies over 90%.
Great.
And I don't know of anybody who's currently building a counterflow heat exchanger, but that's the next stage there, I believe.
Good, good. So I think the exciting thing that I get from our discussions is that, Canada has been a leader thanks to people like you and the National Research Council, Government of Saskatchewan. Canada has been a leader in these very high performance buildings, low carbon buildings, very comfortable and healthy buildings. And it sounds to me when we talk about the next generation window or HRV, that Canada could be stepping up and being the leader again and in manufacturing these for a global market.
I think so, yes.
We also have to get the manufacturing of blower doors back to Canada. if nothing more, just to honor you. We need a manufacturer in Canada, people. So it's that time where we've run out of time, Harold. And I know I'm just looking at the comments. People are really in awe of your lifetime of achievement and very appreciative how you're not resting on your laurels. You're still teaching us things today. I've learned an awful lot more today. Thank you. And on behalf of everybody who's here, and everybody around the world who's been involved with high performance buildings, thank you for a lifetime of dedication to solving those prickly problems about how we ventilate, how we create air tightness, how we insulate, all of the key aspects of Passive House. So thank you. And we'd like to do this again. We'll do this again in future because I'm sure there's lots more you'd be able to teach us. But thanks for today. We appreciate it. And thank you everybody for being on this presentation. I just want to tell the audience though, a couple of things. I want to tell you about our Tower Retrofit Symposium. We know that if governments are going to get to our GHG emission reduction targets, that includes deep energy retrofits. We're working with the Tower Renewal Partnership to bring you this Tower Retrofit Symposium, September 22nd to 23rd. We'll have great projects from across the country, technical experts telling us how to retrofit towers so that we can reduce energy consumption. So early bird tickets are available now. You can get all sorts of information on our website, passivehousecanada.com. And before I go, the next slide. Great. The next slide, we have Oscar Fletchus is going to be my guest September the 8th for our next building conversation. Some of you may know Oscar. He's a great architect, a great teacher, and I look forward to having a conversation with him September the 8th at 12 noon EST. Next and final slide. write down passivehousecanada.com if you want more information about any of the things we're doing. We have all types of education for you, all types of training for you to help you build those high performance passive houses, passive house buildings that we know are needed. So there's our website, there's our phone number, there's more information. Thanks again, Harold, for your time today. And thank you to everyone who joined us. Have a great week, folks, and be safe. Take care for now. Bye-bye.
Goodbye.